Hey everyone, how goes it, and welcome back to Computer Science 311. Today we're going to discuss CPU scheduling. CPU scheduling is the basis of multi-programmed operating systems. By switching the CPU among processes, the operating system can make the computer more productive. On modern operating systems, it is kernel-level threads, not the processes, that are in fact being scheduled by the operating system. However, the terms process scheduling and thread scheduling are often interchangeable. Now, in a system with a single CPU core, only one process can run at a time. Others must wait until the CPU's core is free and can be rescheduled. The objective of multi-programming is to have some process running at all times to maximize the CPU utilization. A process is executed until it must wait, typically for the completion of some I/O request. In a simple computer system, the CPU just sits idle. All this waiting time is wasted. No useful work is accomplished. With multi-programming, we try to use this time productively. Several processes are kept in memory at one time. When one process has to wait, the operating system takes the CPU away from the process and gives the CPU to another process. Process execution consists of a cycle of CPU execution and an I/O wait. Processes alternate between these two states. Process execution begins with a CPU burst. That is followed by an I/O burst, which is then followed by another CPU burst, then another I/O burst, and so on and so forth. Eventually, the final CPU burst ends with a system request to terminate execution. Although they vary greatly from process to process and from computer to computer, they tend to have a frequency curve similar to the one that you see here. The curve is generally characterized as either an exponential or a hyperexponential, with a large number of short CPU bursts and a small number of long CPU bursts. An I/O-bound program typically has many short CPU bursts. On the other hand, a CPU-bound program might have a few long CPU bursts. This distribution can be important when implementing a CPU scheduling algorithm. Whenever the CPU becomes idle, the operating system must select one of the processes in the ready queue to be executed. The selection process is carried out by a CPU scheduler, which selects a process from the processes in memory that are ready to execute and allocates the CPU to that process. However, note that the ready queue is not necessarily first in, first out. There are many different variations of queues that we can implement for this. CPU scheduling decisions may take place under the following four circumstances. First, when a process switches from the running state to the waiting state. So, for example, as a result of some sort of I/O request or invocation of wait for the termination of a child process. 2. When a process switches from the running state to the ready state. For example, when an interrupt occurs. 3. When a process switches from a waiting state to the ready state, for example, at the I/O completion. And finally, when a process terminates. For situations 1 and 4, there is no choice in terms of scheduling. A new process, if one exists in the ready queue, must be selected for execution. When scheduling takes place only under circumstances 1 and 4, we say that the scheduling scheme is non-preemptive or cooperative. Now, otherwise, it is preemptive. Under non-preemptive scheduling, once the CPU has been allocated to a process, that process keeps running until it releases either by terminating or switching to the waiting state. Virtually all modern operating systems, including Windows, Mac OS, Linux, and Unix, use preemptive scheduling algorithms. Unfortunately, preemptive scheduling can result in bad synchronization problems, like for instance a race condition, whenever data is shared among several processes. Consider this case. We have two processes that share some data. While one process is updating the data, it is then preempted so that the second process can run. However, the second process then tries to read the data, which now is in an inconsistent state. We're going to explore this more in a future lecture. A very important component involved in CPU scheduling is called the dispatcher. The dispatcher is the module that gives control of the CPU's core to a process. Now, doing this involves the following: switching context from one process to another, switching to the user mode, or jumping to the proper location in the user program to resume that program. The dispatcher should be as fast as possible, since it is invoked during every context switch. The time that it takes for the dispatcher to stop one process and start another running process is known as dispatch latency. As we can see to the side here, process 0 is executing, then the context is switched where we have to save the state, then restore the state of another process, process 1, and then start that. The space between process 0 executing and process 1 executing is the dispatch latency. Different CPU scheduling algorithms have different properties, and the choices of a particular algorithm may favor one class of processes over another. Many criteria has been suggested for comparing CPU scheduling algorithms. Which characteristics are used for comparison can make a substantial difference in which algorithm is judged to be best. This criteria includes the following: CPU utilization. We want to keep the CPU as busy as possible. Conceptually, CPU utilization can range from 0 to 100%. Now, in a real system, it should range from about 40% to about 90%. Throughput. If the CPU is busy executing processes, then work is being done. One measure of work is the number of processes that are completed per time unit, called the throughput. For long processes, this rate may be one process over several seconds. For short transactions, it may be tens of processes per second. Turnaround time. From the point of view of a particular process, the important criterion is how long it takes to execute that process. The interval from the time of submission of a process to the time of its completion is the turnaround time. Turnaround time is the sum of the period spent waiting in the ready queue, executing on the CPU, and doing I/O. Waiting time. The CPU scheduling algorithm does not affect the amount of time during which the process executes or does I/O. It affects only the amount of time that the process spends waiting in the ready queue. Waiting time is the sum of the periods spent waiting in the ready queue. Response time. In an interactive system, turnaround time may not be the best criterion. Often, a process can produce some output fairly early and can continue computing new results while the previous results are being outputted to the user. Thus, another measure is the time from submission of the request until the first response is produced. This measure is called response time and is the time that it takes to start responding, not the time it takes to output the response. Ideally, what we want is maximizing the CPU utilization, maximizing the throughput, minimizing its turnaround time, minimizing waiting time, and also minimizing the response time. Now let's take a look at some process scheduling algorithms. Now, by far, the simplest CPU scheduling algorithm is first come, first serve, FCFS. With this scheme, the process that requests the CPU first is allocated to the CPU first. The implementation of FCFS policy is easily managed with a FIFO queue. When a process enters the ready queue, its PCB is linked onto the tail of the queue. When the CPU is free, it is allocated to the process at the head of the queue. The running process is then removed from the queue. Now, first come, first serve is very easy to write and very easy to understand. However, the negative side of this is the average waiting time under FCFS policy is often quite long. Let's take a look at this example. If the process arrives in the order P1, P2, and P3, and are served first come first served order, we get the result shown in this Gantt chart. A Gantt chart is a bar chart that we can use to illustrate a particular schedule, including the start and finish times of each of the participating processes, as we can see here. Now in this example, we can see that process P1's burst time is 24. So in order to get to process 2 and 3, we have to wait for that for a considerable amount of time. Now in order to compare this, we're going to look at the waiting time. So what we're looking at is the waiting time for process 1, 2, and 3. Process 1 arrives first, so it doesn't have to wait, so its waiting time is 0. Process P2 has to wait 24 time units before it can be scheduled on the CPU, and similarly, process P3 has to wait 27 time units before it can be scheduled. So this means the average waiting time is roughly 17 time units. Now let's look at the exact same problem, but in a slightly different order. If process 2 arrives first, followed by 3, followed by 1, then the Gantt chart looks like this. Now we can see that the waiting time for P1 is 6 time units. Waiting time for P2 as it arrived first is 0, and P3 only has to wait 3 time units. So in this case, the average waiting time is only 3. Now this appears much better than the previous case in terms of its waiting time. However, you'll notice that there is a convoy effect, as all the other processes wait for one big process to get off the CPU. This effect results in lower CPU and device utilization that might be possible if the shorter processes were allowed to go first. Now expanding this idea, a different approach to CPU scheduling is shortest job first, SJF. This algorithm associates with each process the length of the process's next CPU burst. When the CPU is available, it assigns to the process that has the smallest CPU burst. If the next CPU burst of 2 processes are the same, then we assume first come first served scheduling is used to break the tie. Now the great thing about shortest job first is this algorithm is provably optimal, in that it gives the minimum average waiting time for a given set of processes. However, shortest job first cannot be implemented at the level of CPU scheduling, as there is no way to know the length of the next CPU burst. Now one approach to this problem is to try to approximate shortest job first scheduling. We may not know the length of the next CPU burst, but we may be able to predict its value. Now also keep in mind, the first 2 scheduling algorithms that we've gone over, first come first serve and shortest job first, are non-preemptive algorithms. In other words, we cannot switch in the middle of one process to a different process. The process has to run till completion before it moves on to the next one. Now, if we were to take a preemptive strategy and combine it with shortest job first, that's called shortest remaining time first, which we'll go over in a little bit. Now, if we take this example and basically we sort this based on the burst time, we can get the shortest job first scheduling here, which gives us the average waiting time of 7 time units, which that is the optimal amount of average waiting time. But again, we can only estimate what that CPU burst is. One way that we could do this is the next CPU burst is generally predicted as an exponential average of the measure of lengths of the previous CPU bursts. We can define the exponential average with the formula. Let T of n be the length of the nth CPU burst, and let tau n plus 1 be our predicted value for the next CPU burst. Then, for an alpha that's between 0 and 1 inclusively, we can then define that the tau of n plus 1 is equal to the alpha times that T of n plus 1 minus that alpha times the tau of n. The value of T of n contains the most recent information, while the tau of n stores the past history. The parameter alpha controls the relative weight of the recent and past history in our prediction. For instance, if alpha is equal to 0, then tau of n plus 1 is equal to tau of n, and the recent history has no effect. On the other side, if alpha is equal to 1, then tau of n plus 1 is equal to tau of n, and only the most recent CPU burst matters. Now, more commonly, alpha is defined as 1/2, so the recent history and the past history are equally weighted. The initial tau 0 can be defined as a constant or as an overall system average. Now, this image shows an exponential average where the alpha is 1/2 and tau 0 is defined as 10. Now, furthering this, the shortest job first algorithm can either be preemptive or non-preemptive. We've only discussed the non-preemptive version. The choice arises when a new process arrives at the ready queue while a previous process is still executing. The next CPU burst of a newly arrived process may be shorter than what is left on the current executing process. Now, a preemptive shortest job first algorithm will preempt or interrupt the current executing process, whereas the non-preemptive shortest job first algorithm will just allow the current process to keep running until it's finished. Preemptive shortest job first scheduling is sometimes called shortest remaining time first. And over here we have an example that includes 4 processes. One thing that we have to keep track of is, of course, the burst time. However, arrival time matters too, because remember, these are being loaded into a ready queue and then scheduled to be running. So we know that process 1 arrives first. Its burst time is 8. And as we can see here, it starts running until process 2 arrives at time unit 1. Now, as this is going from 0 to 1, now the burst time remaining for process 1 is 7. However, 4 is less than 7. So in this version of an algorithm, which is preemptive, it will context switch from process 1 to then process 2, simply because 2 has a shorter burst time. Then, at time unit 2, process 3 arrives with a burst time of 9. However, as this has been already running for one time unit, its burst time remaining is 3, and 3 is much lower than 9, so we keep running process 2. Then process 4 arrives at time unit 3. Now once again, process 2 has now been running for 2 time units, where it has a burst time remaining of 2. Now when process 4 arrives, it has a burst time of 5. 2 is less than 5, so we don't preempt, and we allow process 2 to keep running. Now that all of the processes have arrived, we have to start scheduling what is the shortest remaining time. And obviously, process 4 has a time unit of 5. Process 1 has a time unit of 7, because it's already run one time unit. And also, process 3 has the longest burst time of 9. So then we schedule process 4 next. It runs until completion. Then we schedule process P1 to run until completion. And then finally, we schedule process 3 that runs until the end. We can then calculate its average waiting time as 6.5 time units. However, if we were to do this with the shortest job first scheduling, this would result in an average waiting time of 7.75. In this example, the preemptive algorithm shortest remaining time first performed a little better than the non-preemptive shortest job first. Another approach that we can take is a preemptive algorithm called round robin. The way this works is it's a scheduling algorithm that is very similar to first come first serve, but preemption is added to enable the system to switch between the processes. How this works is a small time unit called a time quantum or time slice is defined. A time quantum is generally between 10 and 100 milliseconds in length. The ready queue is treated as a circular queue. The CPU scheduler goes around the ready queue, allocating the CPU to each process for that time interval, in other words, for that time quantum. The performance of the round-robin algorithm depends heavily on the size of that time quantum. At one extreme, if the time quantum is extremely large, the round-robin policy is the same as first-come, first-serve. In contrast, if the time quantum is extremely small, Then the round-robin approach can result in a large number of context switches, and as we know, this is just pure overhead. Here's an example of round-robin where the time quantum is 4. Notice when process P1 arrives, it runs for that time quantum, 4 units. It is then preempted and then switches over to process 2, which runs for almost the entire time quantum. As its burst time was only 3, and our time quantum was 4, it finishes a little bit early, and then it moves on to the next one, P3. P3, just like P2, it only runs for 3 time units given that the time quantum was 4. Now after that, the only thing that is left inside of our queue is process 1, and basically this keeps running until the end as there's no more processes that can preempt it to be scheduled. Now once again, that time quantum matters a great deal. Assume, for example, that we have only one process of 10 time units. If the quantum is 12 time units, the process finishes in less than 1 time quantum with no overhead. Now taking the same example, if the quantum is 6 time units, the process requires 2 quanta, resulting in a context switch. If the time quantum is really small, like 1 time unit, then 9 context switches will occur, slowing down the execution of the process greatly. Again, context switching is pure overhead. In addition to that, turnaround time is also dependent on the size of the time quantum. As we can see here, the average turnaround time of a certain set of processes does not necessarily improve as the time quantum size increases. In general, the average turnaround time can be improved if most processes finish their next CPU burst in a single time quantum. For example, given 3 processes of 10 time units, each has a quantum of 1 unit. The average turnaround time is 29. If the time quantum is 10, however, then the average turnaround time drops to 20. If context switch time is added in, the average turnaround time increases even more for a smaller time quantum since more context switches are required. We've alluded to this before because the shortest job first algorithm is a special case of a general priority scheduling algorithm. A priority can be associated with each process, and the CPU is allocated to the process with the highest priority. Equal priority processes are scheduled in first come first serve order. Now, a shortest job first algorithm is simply a priority algorithm where the priority, P, is the inverse of the predicted next CPU burst. The larger the CPU burst, the lower the priority, and vice versa. Priority scheduling can either be preemptive or non-preemptive. When the process arrives at the ready queue, its priority is compared with the priorities of the current running processes. A preemptive priority scheduling algorithm will preempt the CPU if the priority of a newly arrived process is higher than the priority of the current running process. On the other side, a non-preemptive priority scheduling algorithm will simply put the new process at the head of the ready queue. Here we have an example of priority scheduling. Now we assume that all these processes have arrived at the same time, given these priorities. As you can see, the priorities are sorted from the lowest number, the highest priority, to the largest number, the lowest priority. Another implementation of priority scheduling can be combined with the concept of round robin. In this way, the system executes the highest priority process and runs the process with the same priority using round robin scheduling. Let's see an illustration of this. Now, looking at this Gantt chart and understanding that the time quantum is 2, we can see that first, the process that is run is process 4 because it does have the highest priority. There's no other process with that priority, so it runs until it's completed. However, process 2 and 3 have the same priority, and with that time quantum 2, you can see that round robin scheduling starts taking effect between processes 2 and 3. Every 2 time units, it switches to the other one, until both of them have completed. Then we move on to process 1 and 5, which also have the same priority, and that is scheduled using round robin using the time quantum of 2. With both priority and round-robin scheduling, all processes may be placed in a single queue, and then the scheduler selects the process with the highest priority to run. Depending on how the queues are managed, there is a big O of N search that may be necessary to determine the highest priority process. Now in practice, it is often easier to separate queues for each distinct priority, and the priority scheduling simply schedules the process in the highest priority queue. This is illustrated over here. This approach is commonly known as a multi-level queue, and it also works well with priority scheduling that is combined with round robin. So if there are multiple processes in the highest priority queue, they are executed in round robin order. A multi-level queue scheduling algorithm can also be used to partition processes into several separate queues based on the process type, as we see here. So for example, a common division is made between foreground, in other words interactive processes, and background, otherwise known as batch processes. These two types of processes have different response time requirements, and so they may have different scheduling needs. Now, in addition to that, there must be scheduling among the queues, which is commonly implemented as a fixed priority preemptive scheduling. So for example, the real-time queue may have absolute priority over the interactive queue. Now looking at the example of this, we have 4 different queues. The first one, which is the highest priority, are real-time processes. The next one are system processes. The next one, interactive processes, and then finally, batch processes. Now each queue has absolute priority over the lower priority queues. No process in the batch queue, for example, could run unless the queues for real-time processes, system processes, and interactive processes were all empty. If an interactive process enters the ready queue while a batch process was running, the batch process would be preempted. Now normally when a multi-level queue scheduling algorithm is used, processes are permanently assigned to the queue where they enter the system. If there are separate queues for foreground and background processes, for example, processes do not move from one queue to another. This is because processes do not change their foreground or background nature. Now this setup has the advantage of low scheduling overhead, but the problem is it's very inflexible. Now what we could do to address this problem is introduce a multi-level feedback queue. Now this allows a process to move between the queues. The idea is to separate the process according to the characteristics of their CPU bursts. If a process uses too much CPU time, it will be moved to a lower priority queue. This scheme allows IO-bound and interactive processes, which are typically characterized by short CPU bursts, in the higher priority queues. In addition, a process that waits too long in the lower priority queue may be moved up to a higher priority queue. This is a form of aging that prevents starvation. Now in general, a multi-level feedback queue scheduler is defined by the following parameters: the number of queues, the scheduling algorithm for each queue, the method used to determine when to upgrade a process to a higher priority, the method used to determine when to demote a process to a lower priority, and the method used to determine which queue a process will enter when that process needs service. The definition of a multi-level feedback queue scheduler makes it the most general CPU scheduling algorithm. It can be configured to match a specific system under design. Unfortunately, it is also the most complex algorithm since defining the best scheduler requires some means by which to select values for all of those parameters. Looking at this concept in more detail, let's take this example. Consider a multi-level feedback queue scheduler with 3 queues, numbered 0 to 2. The scheduler first executes all the processes in queue 0, and only when queue 0 is empty will it execute processes that are in queue 1. Similarly, processes in queue 2 will be executed only if queues in 0 and 1 are both empty. A process that arrives for queue 1 will preempt a process in queue 2. And a process in queue 1 will in turn be preempted by a process arriving in queue 0. Now let's assume an entering process is first put into queue 0. A process in Q0 is given a time quantum of 8 milliseconds. If it does not finish within this time, it is moved to the tail of Q1. In this way, we're demoting it. If Q0 is now empty, the process at the head of Q1 is given the time quantum now of 16. Now, if it doesn't complete, it is preempted and then put into Q2. Now, processes in Q2 are run first come, first served basis, but are run only when Q0 and 1 are both empty. To prevent starvation, a process that waits too long in a lower priority queue may gradually be moved up to a higher priority queue. In a previous lecture, we introduced threads to the process model, and we distinguished between the user level and the kernel level threads. On most modern operating systems, it is kernel level threads, not the processes, that are being scheduled by the operating system. User level threads are managed by thread libraries, and the kernel is unaware of them. To run on a CPU, user level threads must ultimately be mapped to an associated kernel level thread. Although this mapping may be indirect and it may use a lightweight process, an LWP. One major distinction between user level and kernel level threads lies in how they are scheduled. For example, on systems implementing many-to-one and many-to-many models, the thread library schedules user level threads to run on an available LWP. This is known as a process contention scope, a PCS, since the completion for the CPU takes place among threads belonging to the same process. Now on the other side, the kernel uses what's called System Contention Scope, SCS. Completion for the CPU with SCS scheduling takes place among all threads in the system. Systems using the one-to-one model, such as Windows and Linux, schedule threads only using SCS. Now, our discussion thus far has only focused on problems of scheduling the CPU in a system with a single processing core. If multiple CPUs are available, it's called load sharing. Now, this is where multiple threads could potentially be run in parallel. However, scheduling issues become correspondingly more complex when we introduce this. Now, traditionally, the term multiprocessor refers to a system that provides multiple physical processors where each processor contained one single core CPU. However, the definition of multiprocessor has evolved significantly, and on modern computing systems, multiprocessor now applies to the following system architectures: multi-core CPUs, multithreaded cores, NUMA systems, heterogeneous multiprocessing. In the first three examples, we concentrate on a system in which the processors are identical, homogeneous. This is in terms of their functionality. One approach to CPU scheduling in a multiprocessor system has all scheduling decisions, I/O processing, and other system activities handled by a single processor. The other processors execute only user code. This is an example of asymmetric multiprocessing, and it's simple because only one core accesses the system's data structures, which reduces the need for data sharing. But the downfall of this approach is that that processor becomes a potential bottleneck, where overall system performance may be reduced. Now, the standard approach for supporting multiprocessors is called symmetric multiprocessing, SMP. Now, this is where each processor is self-scheduling. Scheduling proceeds by having the scheduler for each process examine the ready queue and select a thread to run. Note that this provides two possible strategies for organizing the threads that are eligible to be scheduled. Number one, all threads may be in a common ready queue. Or number two, each processor may have its own private queue of threads. Virtually all modern operating systems support SMP, and this includes Windows, Linux, Mac, as well as a lot of mobile systems including Android and iOS. Now, traditionally, SMP systems have allowed several processes to run in parallel by providing multiple physical processors. However, most contemporary computer hardware now places multiple computing cores on the same physical chip, and this results in a multi-core processor. Each core maintains its architectural state and thus appears to the operating system to be a separate logical CPU. SMP systems that use multi-core processors are faster and consume less power than systems in which each CPU has its own physical chip. Now, this introduces problems that might complicate multi-core processing scheduling. When a processor accesses memory, it spends a significant amount of time waiting for that data to become available. This situation is called a memory stall, and this occurs primarily because modern processors operate at a much faster speed than the memory. In order to remedy this situation, many recent hardware designs have implemented multi-threaded processing cores in which 2 or more hardware threads are assigned to each one of the cores. That way, if one hardware thread stalls while waiting for memory, the core can switch to another thread, as we can see here. From an operating system perspective, each hardware thread maintains its architectural state, such as an instruction pointer and a register set, and thus appears as a logical CPU that is available to run software threads. This technique is known as chip multithreading, CMT. Here, the processor contains 4 computing cores, with each core containing 2 hardware threads. From the perspective of the operating system, there are just 8 logical CPUs. It is important to note that the resources of the physical core, such as caches in the pipeline, must be shared among its hardware threads, and therefore, a processing core can only execute 1 hardware thread at a time. Consequently, a multi-threaded multi-core processor actually requires 2 levels of scheduling, as we could see here. This illustrates a dual-threaded processing core. On one level are the scheduling decisions that must be made by the operating system, as it chooses which software thread to run on each hardware thread, the logical CPU. For all practical purposes, such decisions have been the primary focus of this chapter. Therefore, for this level of scheduling, the operating system may choose any scheduling algorithm, including those described before. The second level of scheduling specifies how each core decides which hardware thread to run. There are several strategies to adopt in this situation. One approach is to use a simple round-robin algorithm to schedule the hardware thread to each processing core. Note that the 2 different levels of scheduling shown here are not necessarily mutually exclusive. In fact, if the operating system scheduler is made aware of the sharing of processing resources, it can make more effective scheduling decisions. On SMP systems, it is important to keep the workload balanced among the processors to fully utilize the benefits of having more than one processor. Otherwise, 1 or more processors may sit idle while other processors have a high workload. Load balancing attempts to keep the workload evenly distributed across all processors in an SMP system. It is important to note that load balancing is typically necessary only on systems where each processor has its own private ready queue of eligible threads to execute. On the other side, on systems with a common run queue, load balancing is unnecessary. Because one processor becomes idle, it immediately extracts a runnable thread from the common ready queue. There are 2 general approaches to load balancing: push migration and pull migration. With push migration, a specific task periodically checks the load on every processor, and if it finds an imbalance, it then evenly distributes the load by moving, or pushing, threads from the overloaded processor to an idle or a less busy processor. On the other side, pull migration occurs when an idle processor pulls a waiting task from the busy processor. Push and pull migration need not be mutually exclusive either, and are in fact often implemented in parallel on load balancing systems. Now let's consider what happens to cache memory when a thread has been running on a specific processor. The data most recently accessed by a thread has populated the cache for that processor. As a result, successive memory access by that thread are often satisfied in cache memory. Now consider what happens if the thread migrates to another processor, say due to load balancing. The contents of cache memory must be invalidated for the first processor, and the cache for the second processor must be repopulated. Because of the high cost of invalidating and repopulating caches, most operating systems with SMP support try to avoid migration of a thread from one processor to another, and instead it attempts to keep the thread running on the same processor to take advantage of this cache. This is known as processor affinity. That is, a process has an affinity for the processor on which it's currently running. It wants to stay on that processor. Processor affinity takes several forms. When an operating system has a policy of attempting to keep a process running on the same processor, but not guarantee that it will do so, then we have a situation called soft affinity. Here the operating system will attempt to keep the process on that single processor, but it is possible for the process to migrate between processors during load balancing. In contrast, some systems provide system calls that support hard affinity, thereby allowing a process to specify a subset of the processors in which it can run. Many systems provide both soft and hard affinity. For example, Linux implements soft affinity but also provides the system call, which has hard affinity by allowing threads to specify the set of CPUs. Taking a look at this, the main memory architecture of a system can affect the processor affinity as well. As we can see here, non-uniform memory access, NUMA, where there are two physical processing chips, each with their own CPU and local memory. Although a system interconnect allows all the CPUs in a NUMA system to share one physical address space, a CPU has a faster access to its local memory than the memory local to another CPU. If operating system CPU scheduler and memory placement algorithms are NUMA aware and also work together, then a thread has been scheduled onto a particular CPU and can be allocated memory closest to where that CPU resides, thus providing thread the fastest possible memory access. Now we have been generally addressing CPU scheduling. However, there are some real-time systems where we have to really consider how the CPU is scheduled. CPU scheduling for a real-time operating system involves very special issues. In general, we can distinguish between soft real-time systems and hard real-time systems. Soft real-time systems provide no guarantee as when a critical real-time process will be scheduled. They guarantee only that the process will be given preference over a non-critical process. Hard real-time systems have stricter requirements. A task must be serviced by its deadline. Service after the deadline has expired is the same as no service at all. We're going to explore several issues related to process scheduling in both soft and hard real-time operating systems. Consider the event-driven nature of a real-time system. The system is typically waiting for an event in real time to occur. Events may arise either in software, such as like a timer expiring, or in hardware, such as a remote control vehicle that's detecting an approaching obstruction. When this event occurs, the system must respond to the service as quickly as possible. We refer to event latency as the amount of time that elapses from when the event occurs to when it is serviced. As we can see right here. Two types of latencies that affect the performance of these real-time systems are interrupt latency and dispatch latency. Interrupt latency refers to the period of time from the arrival of an interrupt at the CPU to the start of the routine that services said interrupt. When an interrupt occurs, the operating system must first complete the instruction it was executing and then determine what type of interrupt occurred. It must then save the state of the current process before servicing the interrupt using specific interrupt service routines or an ISR. Here's an example of interrupt latency. The amount of time required for scheduling a dispatcher to stop one process and start another one is called dispatch latency. Providing real-time tasks with immediate access to the CPU mandates that real-time operating systems minimize this latency as well. The most effective technique for keeping dispatch latency low is to provide preemptive kernels. In this diagram, it demonstrates dispatch latency. The conflict phase of the dispatch latency has two major components. Number one, preemption of any process running in the kernel. And number two, release by low priority processes of resources needed by a high priority process. Following the conflict phase, the dispatch schedules the high priority process onto an available CPU. The most important feature of a real-time operating system is to respond immediately to a real-time process as soon as that process requires that CPU. As a result, the scheduler for a real-time operating system must support a priority-based algorithm with preemption. Note that providing a preemptive priority-based scheduler only guarantees soft real-time functionality. Hard real-time functionality must further guarantee that real-time tasks will be serviced in accordance to their deadline requirements and making sure such guarantees require additional scheduling features. Now, before we proceed with the details of individual schedulers, we must define certain characteristics of the process that are to be scheduled. First, the processes are considered periodic. That is, they require the CPU at a constant interval, and otherwise known as periods. Once a periodic process has acquired the CPU, it has a fixed processing time, which we'll call T, and also a deadline, which we'll call D, by which it must be serviced by the CPU. The relationship of the processing time, the deadline, and the period can be expressed as 0 is less than or equal to that T, which is less than or equal to that D, which has to be less than or equal to the P. The rate of a periodic task is 1 over P. Schedulers can take advantage of these characteristics and assign priorities according to the process's deadline or the rate requirements. Now, looking at some specific algorithms, we have this rate monotonic scheduling algorithm that schedules periodic tasks using a static priority policy with preemption. If a lower priority process is running and a higher priority process becomes available to run, it will preempt the lower priority process. Upon entering the system, each periodic task is assigned a priority inversely based on its period. The shorter the period, the higher the priority. The longer the period, the lower the priority. The rationale of this policy is to assign higher priority to tasks that require the CPU most often. Another approach is called earliest deadline first scheduling. This scheduling assigns priorities dynamically according to their deadline. The earlier deadline, the higher the priority. The later the deadline, the lower the priority. Under EDF policy, when a process becomes runnable, it must announce its deadline requirement to the system. Priorities may now have to be adjusted to reflect the deadline of the newly runnable process. Now, we have to note that this differs between rate monotonic scheduling, where the priorities are always fixed. Another approach is called proportional share. These schedulers operate by allocating T shares among all applications. An application can receive N shares of a time, thus ensuring that the application will have N over T of total processing time. Proportional share schedules must work in conjunction with admission control policies to guarantee that the application receives its allocated time share. An admission control policy will admit a client requesting a particular number of shares only if the sufficient shares are available. In this chapter, we have discussed how an operating system can schedule processes to run. The main goal is to utilize the CPU as much as possible with very little waiting time. We introduced several different algorithms, both preemptive and non-preemptive, to address these situations. We then went further to discuss how threads are scheduled as well. And finally, we started looking at real-time systems and how their schedules are affected by their unique constraints. With all that being said, I'll see you next time.